Greetings and welcome back to Physics with Captain Rod. I'm making this video to help you out with numbers 5, 7, and 8 on your Unit 2 homework. So some things I'd like to just kind of review here a little bit that are going to show up over and over and over in this type of section here. First of all, right, acceleration, remember, what is it? Rate that velocity changes. I'm just going to acronym that. I'm not going to write it all out. And this is how it's calculated, delta V over delta T. Another important thing, Newton's second law, net force equals mass times acceleration. That's going to show up in this homework quite a bit. So let's chat about number 5. It says a jet aircraft with a mass of 4,300 kilograms has an engine that exerts a force equal to 59,600 newtons. So when you're working these problems, start with a picture. We've got a jet and it is apparently taking off. Now your pictures don't have to be Picasso's, just, all right, a jet or plane or something, that's good enough. Right? And the airplane, is the engine is pushing the jet forward, so we might even put a force vector in this for this, right? Now, remember, hopefully, if you've had the Unit 1, there's a way that we can kind of show in the picture that something's speeding up. That's the motion diagram stuff. So remember, click, 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 click. So this point on this plane here, just using the dot to represent the plane, these are going to get bigger and bigger and bigger. Remember, these are delta x's. These are changes in position. So this is our way to show in the picture that that plane is going to be speeding up. So write down all of the relevant information. So the mass of the plane, I'll just put that right over here. In this example, it says 4,300 kilograms. Yours may be different because I set this up to, so that everybody has different numbers. And the force given in the problem, 59,600 newtons. So you got to get in the habit when you're working these homework problems. Draw the pictures. Write down all of the relevant information. Okay, now you can start working the problem. And what you want to do is start with Newton's second law because there's a force given and a mass given. So you should be able to find the acceleration. Now, to answer the rest of the questions, when it says, what is the speed after it accelerates for 9 seconds, right? Well, once you know the acceleration, write this out. What is the acceleration? It's delta V over delta T. And this is something that you calculated in Part A. This is given in the problem. That's going to allow you to calculate this, your change in V. That will tell you how much that plane has sped up. Then it says, how far did it go? Right? Once you have that change in velocity, draw a velocity graph. That's Unit 1 stuff. All right, so a reminder, that's a graph of velocity against time. And then ask yourself, at t equals 0, how fast is the plane moving? And then that should allow you to put a point on this graph, but I'm not going to do that for you. And then 9 seconds later, how fast is the plane moving? Now, in my problem, this said 9 seconds. Your problem, it might be a different number, but once you have that change in V, that should allow you to put another point on this graph, connect the dots via our standard constant acceleration assumption, and when it says how far, ask yourself, remember, the delta x, what property of this graph gives that? And I'm going to let you, hang on that, I guess, if you don't know the answer. I got lots of videos on how to calculate displacements or distances using velocity graphs. So that should get you through number 5. Let me get rid of this stuff here and we'll talk about number 7. Okay. Let's see. 7, it says a sprinter with a mass of 79 kilograms accelerates from 0 to 7 meters per second in 3 seconds. So start by writing the data down. In my example, a mass, 79 kilograms, was given in the problem. 0 meter per second to 7 meter per second in 3 seconds. Picture wouldn't hurt. So we have a sprinter. Again, your picture does not need to be super art. That one's because that one looks like a 3-year-old, but that's okay. And presumably they're probably starting from rest. So do your motion diagram, all right? Here's the dot, dot to represent the person, and they're going to be speeding up. Right? So they're accelerating in this direction. Now, you should be able to calculate the acceleration from these numbers, because remember, acceleration is change in v over change in t. And then part B, what is the net force on the runner? Well, once you have the acceleration, write out Newton's second law. And you're given a mass and you're calculating an acceleration. Should be good to go there. How far does the sprinter run in 3 seconds, right? Draw a velocity graph. I don't want to give this away, but ask yourself, when t is 0, what is v? And I'm not going to tell you what that is. Look at the physical problem and you make a decision. Put that on the graph. And then this one's given to you. 3 seconds later, the velocity is this, right? Put that on the graph. Connect the dots. Then you can calculate the delta x by, and I think I won't give this away here. I got lots of videos on how to do that, how to find those change in positions from those graphs. So that should get you through number 7. Let's chat about 8. Let's see, a baseball being caught goes from 37 to 0 meter per second in 0.004 seconds. So let's start with a picture. All right, so there's a ball. It's a baseball. And that ball is moving pretty fast. In fact, that was given in the problem. It's starting at 37 meter per second. You may have a different number. Now this ball is getting stopped. Now I'm going to exaggerate the distance. If they actually catch the ball, it's not going to move very far. But I'm going to kind of exaggerate the distance with my motion diagram. So dot, dot, dot. And again, these dots are getting closer because of the velocity of the ball decreasing. And this is what we call a delta x, a change in position. This has been greatly exaggerated, though. If somebody caught this with a glove, that ball would not move more than an inch or two and would stop. But it's okay to exaggerate something in your picture for the sake of clarity. Okay, now it starts by asking for the acceleration. So you just have to know, how is acceleration calculated? Well, there's how it's calculated. And when you calculate the delta v, remember that change in velocity is v final minus v initial. Change in anything is always final minus initial. So be sure you get the 37 meter per second in the correct place. That's going to be important for your answer here. And then just ask yourself, what is the v final? It's maybe not stated in the problem, but, well, actually, yeah, it is stated in the problem. 37 meter per second to 0, it says. So time also given in the problem. Now, one thing that you need to realize is, that delta t in my example, that says 0.004 seconds. Make sure you get the correct number of decimals here. You are going to get a pretty darn large number for that acceleration, large in magnitude at least. That's okay if you do. Now, the next part where it says, what is the acceleration in g's? Well, gravitational acceleration is 9.8 meter per second squared, or I like to approximate that to 10. So what that means is if you had an acceleration of 20 meter per second squared, that's what's called a 2g acceleration because it's 2 times this. A 30 meter per second squared is called a 3g acceleration, and so forth. And notice if you take this and divide by this, you get 3. So when you get this acceleration, divide it by 9.8, that will tell you how many g's that is. Part B, what is the size of the force acting on it? So that's a Newton's second law question. Acceleration is given, mass given in the problem. Actually, the acceleration wasn't given, but you should have calculated it earlier. Let's talk plus and minus signs. For part A, where it says what is the baseball's acceleration, and you notice it says in the question, indicate the direction with a sign in your answer. So we are inherently calling, in my picture, right positive. You'll have to think about plus and minus on the acceleration. But for part A, but for part B, where it says what is the size of the force acting on it, the word size is a magnitude only. You shouldn't need to worry about plus or minuses for part B. So that should get you through those 3 problems. Yeah, hope all is well. Have a great day.